So are there any questions about the homework assignment? I saw 4 people turning in already, so I'm just kind of curious whether there are questions about the homework assignment, any questions about the CNF or any of the transformations that you need to know or need to apply in order to convert something into a CNF. Yep.
One of the bullets that you posted already in CNF?
Sorry?
Out of the 3 bullets, wasn't one of them already in CNF?
Yes. I'm not going to name which one, but yes, one of them is already in CNF. All right, so we are still in propositional logic. We are basically finishing up propositional logic at this point. I believe last time we were talking about proof by resolution. So this is the next homework assignment, but it's not modified for this semester yet. Okay, so do not start working on it because it's not your homework assignment. Your homework assignment is going to be based on your CNF assignment, which is due on Thursday. So you got to have it done first, okay? So on Thursday, what I'll do is I'm going to give you the answer to the CNF assignment. And then for those of you, if you want to use your own solution as the starting point of the resolution homework assignment, that's fine. If you want to use my solution as a starting point of your resolution homework assignment, that's okay as well, okay? So I just want to bring this up, just in case there are any questions about this particular homework assignment. Any questions that I can answer about this homework? Yes?
Wait, why are you giving us the answer though?
What? It's due today.
Huh?
It's not due today. I said I'll give you the answer on Thursday.
Oh, I thought you said you're giving the answer right now. Sorry.
Oh, no.
I was confused.
Nope, on Thursday.
Are you trying to convince the council?
So you have to write it in the LaTeX?
You do not have to write it in LaTeX. You can write it in the format that I outlined below. What?
Making fun of my ass.
Okay. So you can use PQ to represent P and Q. So use multiplication to represent conjunction, and then the disjunction can be represented using using plus. So that's a typical representation in industry as well.
So what about the implication, the right arrow?
You can just use an equal and a greater than combined.
Oh.
Which is what I usually use for the text editor. That's how I would use it too. And then negation is a single exclamation point, which is borrowed from the C syntax. All right. Okay. So if you think that there might be some confusion about priority, you can always use parentheses to indicate which operation should be applied first. Okay, so you have to remember to use parentheses if you're not really sure that I understand the order of the operations, use parentheses. Okay, any other questions? No other questions? Just one more thing to point out before we move on. Your job is to convert these 3 well-formed formulae into a single CNF well-formed formula. Okay, so you have to remember that part. I do not want the answer to be 3 CNF well-formed formulae. I want the answer to be 1 single well-formed formula. Okay, so you got to remember that part. Which is a very easy way to. There's a very easy way to get to that answer once you have the individual CNF. All right. So if there are no questions about this, I'm going to kind of just roll back a little bit to resolution and finish off that slide, and then we'll see if there are any questions about resolution. So any questions about this stuff that we talked about last time, about resolution itself and why it makes sense, why resolution is a sound inference? Are there any questions about that part? Any questions about that part? So that part is okay? All right. Now remember, this proof here is not something that I would test you on. In other words, I'm not gonna, change some part of this proof here and say, okay, it is now incorrect. Find out what is wrong with this proof and fix it. That would be kind of one of the questions that I can possibly ask, right? But I do want you guys to understand how it works. Okay, so try to spend some time. If you kind of look at this and go like, oh, this is a whole bunch of mumbo jumbo. Well, it is not a whole bunch of mumbo jumbo. It's a whole bunch of mumbo jumbo, but it is structured. Okay, there's a meaning to this bunch of mumbo jumbo. So for each step, maybe not this one. So for this one, I think it might be helpful for you to annotate it. So just copy and paste it, somewhere, and then you try to annotate it. Just print it out, okay, and then annotate how we get from one line to the next line. And understanding the transformation that can get you from one line to the next line is going to be helpful for this class. So that's not going to be a graded assignment. I'll just let you guys go ahead and do it on your own. Now the bottom line of this particular inference rule, okay, it's an inference rule because of the rotated T symbol, is there's only one needed. Okay, this is something that we have talked about multiple times, but since the last class was 5 days ago and it was a long weekend, I'm guessing like 65.7% of this class has already forgotten the big picture of this stuff, right?
It's pretty accurate.
Pretty accurate, right? I think the margin of error is plus or minus 0.56%. Okay, so the big picture is we don't want all those inference rules, because with the previous approach we have a whole list of inference rules. I would say probably in the order of 20-ish inference rules, and those are all sound. They're all complete. Okay, which means the system would be able to syntactically derive any well-formed formula that we can. But there's a problem. Because there are so many choices to choose from, how is the computer going to choose which one to apply? It doesn't know. So it is more likely it will find the wrong inference rule to use. In other words, it is not wrong in the sense that it will give you a wrong answer. It just doesn't get you closer to the theorem that you're trying to prove. With this one, we can choose any way we want and we'll still be okay, because there's only one rule. You cannot choose the wrong rule. Now, what you use it on can be quote unquote wrong. In other words, you can be applying this on something that would not give you something that is closer to the solution. But that's okay, because you can only be moving in the wrong direction so many times. It is a finite number. Okay. So the next thing is to talk about what are we going to do with resolution. Resolution itself is kind of cool, because what it means is you can use two disjunctions, and as long as one has a variable that is not negated and the other one has the negated version of the same variable, you can quote unquote concatenate the rest of it. So the rest of the original well-formed formulae can now be concatenated, but the result from the concatenation is the variable where it is not negated on one side and negated on the other side is gone. In other words, the result is going to be a little bit shorter than just the straight concatenation of the two. Now, why is that important? It is important because you started off with three things on the left-hand side. You started off with phi, psi, and rho. What do you end up with on the right-hand side? Only two things. One of those things is gone, which basically means if you keep applying this type of resolution, eventually you will either run out of stuff, okay, there's no new result anymore, or you end up with a zero or false, which is contradiction. That's the beauty of resolution, okay? It's finite, how much time it takes to get to the point where you can say, I'm giving up because the theorem cannot be proven, or here it is, okay? We have just proven the theorem. The number of steps to get to that point is finite. There's always an end to this particular algorithm. Okay, so that's really important. In order to prove using resolution, we have to change the perspective a little bit instead of using a direct proof, which means you start off with the axioms and everything that you know to be true, and you try to use implication to connect all the way to the end, which is the theorem that you want to prove, you change it around and you say, well, how about this? I negate the theorem that I'm trying to prove. I put it into what we know as iota, which is the things that are known to be true, and this time I want to get to a contradiction. Okay, remember that picture? I'm going to draw that picture one more time. Okay, it's an easy picture to draw. So what we want to do initially, okay, with a direct proof, this is what a direct proof looks like. So a direct proof start off with the iota set. Okay, so the iota set gives you well-formed formulae. So each one of these is representing a well-formed formula that is known to be true. Okay, don't ask me why it is true. It is known to be true. It is in iota. And here is the theorem that we're trying to prove. So with a direct proof, what we're trying to do is to form a chain of implications. Okay, so here we have one implication combining two well-formed formulae into one. Here's another one, and this one is, I mean, obviously this is really just for illustration purposes. Okay, but at some point, I'm gonna pick out one more here, combine it over here. So at some point, we can now imply the theorem that we're trying to prove. This is a direct proof. A direct proof is always moving forward using implications, but the big part is what do we start off with, and where's our destination? The destination is the theorem to be proven, and then the starting points are whatever is in the iota set. That's a direct proof. The problem with a direct proof is you can move on, into the wrong direction. There's still implications, but they can lead you further and further away from the theorem that you try to prove. And unless you're really experienced with proving mathematical theorems, you probably will have a hard time, trying to find out, okay, what do I use, what do I apply, so that I can be closer to the theorem that I'm trying to prove. On the other hand, proof by contradiction is a little different. So we'll call this theorem, we'll give it a name, we'll call this psi. Okay? So with proof by contradiction, we still start with everything in iota. So everything that is known to be true will still be our starting point. 1, 2, 3, 4, 5. I used 5 dots over there. I'm going to use 5 dots as well over here. So these are all starting from iota itself. These are known to be true. But what we'll also do in this case is we'll negate phi. The very theorem that we're trying to prove is now negated as a starting point. Okay? But this time, we're not trying to get to psi anymore. Because we already put the negation of psi here. What we're trying to do is to get to a false, which is the contradiction. Now, how do we get there? There's still implications. Okay, so you still combine things using implications, and this time you have one extra thing that you can use for implications. So as long as you can do the implications and eventually lead to a conclusion of false, then you have just proven that the theorem itself has to be true. If the negation of the theorem leads to a contradiction, then the theorem itself has to be true. Yep.
Do we always use implication to prove a theorem?
Yes. That's basically what a theorem is. A theorem is basically a way to look at things that can be implied by everything that you know to be true as a starting point.
So on the next homework, do we use the theorem that we came up with this assignment, and then we prove it?
For the next homework assignment, I will have to give you the theorem that you are going to prove. Because with the homework, I'm just giving you everything in iota at this point. I have not given you the actual theorem that I want you to prove, so you cannot quite start doing it yet, because I have not shown you what is psi in this case. Go ahead.
You said in the homework for next time though, you actually gave us, you told us just to prove Q.
Prove.
Q. Like you gave us a variable Q, and you gave them all.
But that's not, but that's from the previous semester.
Oh.
So the one that we're going to do for this semester is going to be different.
Oh. That's probably how we.
Yep, yep. So the homework has not been adjusted yet, for this semester. Now I can possibly trick you, okay? Since I told you that I might do this, it's not a trick anymore. But I might give you a well-formed formula that is not a theorem, based on the facts that I gave you in the current homework assignment. You still have to come up with a conclusion. You still have to say there's no more resolution to be done anymore. But since we cannot get to a false, which is a contradiction, then the answer is the theorem is not a theorem. The proposed theorem is not a theorem. You will still come to a conclusion. That is the beauty of resolution, because it can only take a finite number of steps to get to the point where you can either say with certainty that this is a theorem because you got to a contradiction, or psi is not a theorem because there's no way you can prove that there's no way to get to a contradiction. Yes?
So iota is a bunch of well-formed formulas,
Yes.
and then you connect them through implication.
Yes, but these implications are special because these implications here with general propositional calculus, these can be any one of those 20 or 30-ish inference rules. All of these are resolution. Because what we do is we look at this entire thing, including the negation of psi, and we combine everything into one gigantic conjunctive normal form, well-formed formula. Okay? Now, when I say CNF, I negate, I neglect to mention it's a well-formed formula, but this is one gigantic conjunctive normal form, well-formed formula.
So the CNF is composed of iotas.
The CNF will compose of everything in iota along with the theorem, the negation of the theorem that you're trying to prove. But each step is one application of resolution. Okay. So are there any questions about, how everything fits in? Any questions about the mechanism of proof by contradiction? Because that sounds like an oxymoron, right? We get to a contradiction, and how come we are actually proving a theorem by getting to a contradiction? Are there any questions about that aspect of proving a theorem? No questions about that? All right.
Hey, I'm sorry to interrupt your class.
Yes.
Is there a Catherine Adler?
She is missing today. She's not here.
Okay, perfect. Thank you.
Mm-hmm. I believe so, because I think I remember Kathleen from last semester. So, and I believe she's not here. Look under the desks. Alrighty. So, any questions about this stuff here? Now, proving using resolution has, this little thing here, a corollary, which is basically a small theorem. So the small theorem is basically just saying, okay, can we establish that this is always true? Because anything that is always true is useful, okay? And as it turns out, this is always true. If you know that P implies Q is always true, then you can always, make a conjunction out of this and out of this as well. As long as your conjunction involves exactly the same thing on both sides, then the implication will still be true. And we talked about this in the previous class using a truth table. Okay? Are there any questions about this part? The truth table is one way to prove something, but then we can always use an actual direct proof as well. Now this is a direct proof. Now the way this is a direct proof is also bidirectional because you can go in both directions. well, actually, I take it back, it's not in both direction, it is only going in one direction for the most part. So from here we can go to here, and then from here we can go to here. So some of these steps are bidirectional, but some of these are not bidirectional. But are there any questions about these derivations? So once again, just for practice purposes, it is probably a good idea to look at this, print it out, and then try to figure out, what did I do to move from one row to the next row? Okay, which rule did I use? Which rule in Boolean algebra did I use to go from one step to the next? I'll pick, just 2 rows as an example. I'm going to pick these 2. Okay, so how did I go from here to here? What rules did I use in this case? I did 2 transformations. Okay, on one side I applied De Morgan's law, so I can move the negation into the inside of the disjunction. So we have double negation of P, which is just P itself, because double negation cancels itself. And then we have the negation of Q, but then we also have to change disjunction into conjunction. This is one application of De Morgan's law. On the other side, I distributed the, in this case, I just distributed not P or not R out into the open, because I use the associative law of disjunction, so that I can just get rid of this pair of parentheses, because it is a disjunction here, it is also a disjunction here, so parentheses are not needed in this case. Yep.
How do you get the not in front of Q and R?
That's De Morgan's law.
No,
The next line.
The next line? You mean here?
after you remove the parenthesis, you said or, not Q and R.
Okay, so is the question from here to here?
Yes.
Because there's an or outside of the parentheses, there's an or inside the parentheses, right?
Yes.
But because disjunction is associative, and that's why I can dissolve the parentheses and not use the parentheses here at all. It's just like addition, right? A plus B in parentheses plus C is the same thing as A plus B plus C without parentheses. Yeah, go ahead, Shane.
When you dissolve the parentheses, what rule do you state? Do you just say like
Associative?
associative?
Yep.
Or if you like factor them, like do you just say distributive property or something?
Yeah.
Okay.
Yeah, it's not an actual homework assignment, but you have to kind of understand how I derived it. Yep. Go ahead.
After you did the associative property though, you added a negation to the Q and R. Where did that negation come from?
You mean?
Right, if you move the cursor down a little bit, there's that negation. Where did that?
You mean this
right,
negation?
To the right. To the right.
To the right
that-
here?
Yeah, that guy. Where'd that guy come from?
Oh, where this one comes from? That's a good question. That could be a typo, but
So taking it from the beginning of the equation, like above you have not P or Q, and then below it you have
No, because you have to absolutely the same. It's not in the next line.
it's not in the next line, so I think it's a typo. I think that really is a typo, because there's no source of this negation. So I think it's a typo. I'll fix it. So this is in the 1, 2, 3, 4, 5, 6, 7, the 7th row of the equation, right before proof by contradiction. And let's see if we can spot it. So it's right before proof by contradiction, and we're looking for the 7th line, the 7th row. Now there's a quick way to do it, because backslash is how I open a new line in the proof. So what I do is I just look for backslash. Okay, so here's 1, 2, 3, 4, 5, 6. So it will be on this row that we have the extra negation that should not be there. There we go. I think that's the one that we need to take out here. Yep. What? Okay, so let's check whether that's going to be fixed or not. So let's see. Yep, the extra negation is now gone. Thank you. Thanks for letting me know of the extra negation. I have done this for many years, so that's why I can do it relatively quickly. All right, but that's a good exercise. The most tricky part, I can tell you what is the most tricky part of this proof. The most tricky part is here. From just the negation of R by itself, I just added a conjunction out of nowhere, okay? Because any conjunction with a true doesn't really change the meaning of something. So normally we go the opposite way. We say, oh, here's a conjunction with a true, and let's simplify it out of the way. But this turns out to be the really most important step of this entire proof. Okay, this is the one thing that is the most difficult for people to come up with, is to introduce a conjunction with a 1. And then the next one is to take this 1 and say, okay, what can give me a true? Oh, this can give me a true, Q or not Q. These two steps turn out to be the most important steps for this particular proof. Yep.
So how do you know when to use that and when?
That's also a very good question, which is a lot more difficult to understand. Even for me to explain it, it really is just exploring all the different ways. You kind of know where you want to be, and you know you're kind of stuck at a certain point. So you start to explore all the different ways of doing things. And remember, how at the first week of the semester, I told you guys to take a personality test? Yes? No? Okay.
Yes.
Okay, this has to do with your personality. If your personality has extroverted intuition, this is what allows you to do stuff like that. It is the NE in a personality that does that. Okay, I can explain that just a little bit more after I answer that question. Yep.
So, wouldn't we do it anytime we need to introduce a variable that we can like cancel? So like you did it so that you would get the Q or the not Q. So it gave you the ability to add new variables so that you could use it to cancel maybe out other variables that you didn't want. So it's like a tool you can use to get rid of things you don't want.
Right, because what I want to get rid of, or what I want to combine with, is in the end, I wanted to do something, I wanted to end up with this. I want to have a not Q, or Q in here. By combining not Q or Q, it is a true. So I know I wanted to do that. But in order to end up with this, I need to refactor things. In other words, I need to refactor this 1 from not R or R. So this not R and R, is what I need in order to get to this 1. But how do I get this R? There's no R, there's no Q or not R up here. There's only a Q or R. So the only way to introduce a not R into the whole thing is to do, when we do have an R, then we just manufactured the Q as a conjunction into. So that's the trick. So I kind of knew where I wanted to go. I just needed a mechanism that can get me there. Okay, so getting back to personality types, I'm going to spend 3 minutes to explain those 4 letters and how you can connect the MBTI, Myers-Briggs type indicator, into the Jungian, Jung, Carl Jung. Okay, so he's a psychologist. Okay, this is a quick one. So I'm an INTP. Okay, so what you do is you first identify whether your dominant function is introverted or extroverted. So you write this out on one side, and then on the other side, you make a little stack here. And we know that it's going to be IE. This is called the dominant. This is called the auxiliary. This is the tertiary, and this is the inferior. Okay? So basically, this is the strongest function, the second strongest, the third, this is the weakest function, okay? So the introvert applies to the dominant function. So if you're an introvert by MBTI, it means your dominant function has an introvert. They call it, I cannot remember it's kind of like an orientation, this introvert versus extrovert, okay? So we know it's an IEIE. And then with an introvert, this letter is describing one of these two. So we know it's either an NT like this or TN like that. But which way is it? So with an introvert, the perceiving is describing the second strongest function. But out of the two functions, intuition versus thinking, intuition and sensing are called perceiving functions. Thinking and feeling are called judging functions. So since I know my second function is a perceiving function, it can only be N in this case. Now, once I lock down the N, the T has nowhere else to go except at the top. Once you know the top two, the bottom two are basically opposites of the top. N's opposite is S, T's opposite is F. So this is my entire function stack using Carl Jung's function stack. Introverted thinking means I prefer my strongest function is to try to integrate everything logically into an internal framework. Okay, that usually typical explains basically what they call mad scientists. People who derive all kinds of theory to explain the world, but never spend a single moment to apply those theories to actually do anything. Okay, so TI is like that. NE is extroverted intuition, which is a function that explores possibilities. Okay, SI is a memory function. People with an SI up on top, those people have exceedingly good memory as well as well organized. And then FE is extroverted feeling, which is basically sensing harmony or their lack of amongst a group of people. So you can read about all of this stuff here, but for the question that was asked a little bit earlier, proving theorems actually has a lot to do with these two kind of combined, because the TI is the application of logic, boiling everything down to the bare essence of the logic, abstraction. And then NE is the capability of exploring possibilities. So I would say there are two personality types, when it comes to proofs like that, there are two personality types that are exceedingly good at this. One is INTP and the other one is ENTP. ENTP is really kind of like this, except NE is first, TI is second. Is that okay? Is that helping? I cannot change personalities, so in a way it is not helping, but it's explaining, what type of personality is good at what. Okay. So can anyone think of, something that I'm not really so good at? What kind of occupation would not be very good for me? What do you think would require FE, extroverted, feeling?
Therapist.
Therapist, okay, that's one. Counseling, yep, counselor would require that as well. I would say in general, if I want to be a minister, that probably needs a lot of FE as well. Politician, needs a lot of FE. Well, okay, normal politicians, because sometimes we have abnormal politicians that are successful and have absolutely no FE whatsoever. Just kind of steamrollers, right? So anyway, you guys can look this up. There are tons and tons of material online that talks about personality types. And I would also not be so good at anything that requires details or memory. Nope, I do not. It's my third function, which is good for entertainment purposes. That's basically what the third. Okay, the first two are what you rely on a daily basis. Whenever you have to make up your mind to do something, whenever you have to solve a problem, whenever you have to decide on something, this is what allows you to do your daily operation. This one is kind of for entertainment purposes. They say, okay, when you look up these personality, analysis stuff, they say INTP people are nostalgic, and that is where that's how the TI integrates into it. Okay, but it's only for fun. It's like, when I do have time, I like to kind of look back at old pictures of myself or something. Okay, but I'm not going to use my SI. I'm not going to rely on my SI to make important decisions. Yep.
Just for a question. So if that P is a J, then it would be N on top, T on bottom, F on top, S on bottom. Like if they would switch like that.
Yeah, it would switch like that. So FE is here, and then SI is down at the bottom.
Okay.
Yeah, people with this function stack, which are known as ENTPs, are even more scattered than I am. They're also a lot more inventive as well, because their NE is actually first. So this is the primary function, and this is the secondary function. And for me, it is my extroverted intuition is a little bit less strong than my TI. But it's interesting stuff. Okay, just when you have time, take a look at yours. And there are no good or bad personalities. If you look at the 16 personalities, none of them is bad. It is what it is. Okay, every single personality has a place where it is needed, and every personality has significant weaknesses as well. So it is just, but the importance of this stuff in a class like this is you can use it to help guide you to the occupation and career that you are innately good at. Okay? If I want to become an NBA player, that may not be the best decision of my life, right? Well, there you go. Okay, so there you go. There are lots of things that I'm not good at. I just want to avoid making those my career. Okay, so getting back to proof by contradiction. So I already drew a picture of contradiction, and I think this is a good picture to remember. Yes?
On the proof, I was also wondering one of the steps that you did, where you went from a disjunction into implication, like a third of the way down the proof.
A disjunction into an implication. Oh, you mean these two? Between here?
Yeah, because you then later kind of undid the switch from disjunction into implication, because you both go back into disjunction and then simplify it again later down so it's exactly the same as it was prior. And when you go from disjunction to implication, it only changes the left-hand side of the implication, right? Because you're effectively negating it and turning it into.
That is correct.
So I guess my question is why, what are you doing when you do that on the left-hand side?
On the left-hand side?
I guess why?
You mean this part here?
Yeah, I guess kind of like why do the conversion into implication?
That could be a remnant of copy and paste. The lack of detail-oriented stuff is definitely because of the SI being kind of low on the stack. Oh, by the way, for those of you who are really into this or trying to get into this is basically where your consciousness is. In other words, for the most part, your inferior function is below your consciousness, which means it can bite you out of nowhere. You're not aware of that. Okay. But that's probably because of some copy and paste approach. Anything else? In other words, this step is not needed. We could have connected everything from here all the way down here. In other words, these two steps are just not needed, right? These two rows over here, they do not serve any purposes because we got exactly the same thing as both. I have no idea nor recollection of why I did this. So for the most part, you can get rid of those two rows and not impact the proof at all. Any other questions about the proof? Okay, so there are no proofs. So here is a proof by contradiction. So this is proof by contradiction. This is the proof of proof by contradiction. In other words, I am proving that the approach of proof by contradiction works. And it has to do with the smaller theorem that we just looked at over here, because you can do a conjunction with anything as long as you have the original implication. If you add a conjunction with something, as long as it is added to both sides, the implication will still work. Okay? So in order to prove proof by contradiction itself, what we are doing is we are adding the negation of the theorem to both sides. So on one side we have the, okay, let me see if I can find that. Okay, so we want to look at, in this case, psi is representing everything that is known to be true, and then phi is representing the theorem itself. So what we're doing is we are introducing the negation of phi on both sides. And by doing that, one side is going to be introducing the negation of psi. Okay. I'm just looking at the terminology here. The previous called in the assumption that psi, which is the, there we go, okay. Okay, it did it in a slightly different way than what I did in the previous class. Okay, first of all, can we establish this line here? Psi implies phi is exactly the same thing as not phi implies not psi. We talked about this last time. There was actually a proof in both different ways. We proved this by a truth table, and we also proved it by Boolean algebra. How many people kind of remember that part? Okay, so that is established. So once this is established, this part here, then we can add a conjunction with something to both sides, and the implication will still be held. So in this case, we're introducing psi on both sides. So by introducing n psi, okay, on both sides, one side becomes not phi and psi, which is something, but the other side becomes not psi and psi. Not psi and psi has to be a false, which is a contradiction, which basically means we can now say that if this side, which is the negation of the theorem itself, not psi, not phi, and psi, which is the everything in iota, when you combine that stuff into a conjunction, if that implies false, which is the contradiction, then you have just proven that the theorem itself, which is phi itself, is true. Just works out a little differently compared to what I talked about last time. They're both valid. Okay, let me use the whiteboard and see if I can illustrate that. Okay, I can erase this stuff. Just want to make sure I use the same terminology here. So psi implies phi. Okay, so when we look at a grid symbol, it's kind of like, okay, but what is what? This is the stuff from iota. Okay, this is one CNF by combining everything that we have in iota. This is the theorem, or the proposed theorem that we are trying to prove. So if this is actually a theorem, this implication should hold. Is that okay? Okay. Then we can use this and say, well, but we can look at this in a different way. We can say not phi implies not psi. That's just Boolean algebra. Or you can prove it using a truth table. We talked about this proof in the previous class, so I'm not going to repeat that here. But these two statements are exactly the same. They are equivalent to each other. Is that okay? And then we have that theorem that we talked about a little bit earlier, and say, if we already have an implication, you can always just add a conjunction with something. As long as you do it to both sides, the implication will still hold. Okay. So we can say, okay, so let's go ahead and pick something to put here and keep the implication and then put something else to put here as well. The question is, what should I put here? We can pick anything we want, but not everything is going to make a whole lot of sense or help us in this case. So we say, well, what about psi? Okay, so we say the conjunction with psi on both sides. Sure, why not? But that means one side has not psi and psi, which is the false of the contradiction. And then the other side is the negation of the theorem and everything in iota. And this is the proof that proof by contradiction works. Is that okay? And by combining this into CNF and resolution, resolution is just a way of doing the implication. So we want to use resolution to eventually get to a false. And that's how we connect everything. Is that okay? All right. And I think we did go through the first example. Now the question is, how do I know that I can stop at this point? Okay, because in the previous class I already stated that by this time I can say, okay, I cannot derive any other CNFs. Okay, I can apply resolution, but it won't give me anything new. Okay, but how can you confirm that using an algorithm? Any ideas? I mean,
Is there a maximum number of terms? Is there a maximum number of terms? Like you say, hey, when I have this many terms, I know it's smaller.
okay, so when you look at this, we know how resolution works, right? Resolution requires that you have two conjunctions, where on one side you have a variable not negated, on the other side you have the same variable but negated. Then you can combine the rest of the CNFs into a new one. That's how it works. It's just pattern matching, right? So if we just look at this, and we can just apply let's just apply pseudo eyeball algorithm in this case, okay? So how would I go about doing this, okay? I can just look at not P. In other words, I can use a for loop, okay? So I can have two levels, or a little more than that, but I can have two main levels of for loops. The outer level of the for loop is looking at the first CNF out of the entire, the first component of the CNF out of the entire CNF. The second loop is looking at the rest of the CNF and see if I can match. Is that okay? In other words, the outer loop is looking at this thing here, and then the inner loop is looking at everything else. So now I'm looking at this as the outer loop index, and the inner loop index is looking at this. And the question is, can I apply resolution? Well, the answer is yes, we can apply resolution because the one has not P and the other one it has P, so they can, we can combine the R and the Q. But the question is that new? R or Q, which is the result of this application of resolution, is it new? Nope, we got it here already. So that means that resolution, even though it is applicable, it did not give us anything new. Okay, fine. Let's pick out what about this guy and the third one. In other words, I move the inner loop into the next component of the CNF. So I look at this, I look at that and go, can we apply resolution? Yes, we can, because one has R and one has the negation of R. So we end up with not P or not Q in this case after this resolution. The big question is it here already? The answer is yes. It's the second last item. We have it here already. So there's nothing new. So now we move the inner loop into the next one, which is the R here. Cannot resolve with this one. Okay, fine. Move the inner loop to this one here. Not Q, cannot resolve. Move it over here. Yes, we can resolve. Okay, because remember the outer loop is still over here. It is still looking at the first component. So we can now look at the first component. Sorry about that. Let me see if I can do a better job this time. So we are looking at the outer loop is still looking at the first component. The inner loop is now looking at, which one again?
B.
P? Okay, so we can look at this one here and say, yes, we can resolve, but the result of the resolution is a single R. The question is a single R a component of this CNF already?
Yes.
Yep. Okay, so we did not end up with anything new. Then we move on to this one here. We cannot resolve because they both have the non-negative version of R, so we cannot resolve. Then we move on to here. We cannot resolve because both have the negative version of P. And then we move on to here and say, yes, we can resolve. So after we resolve the first and the last one, the P and the not P will cancel out. So we end up with a R or not R. Oh, but that is useless because R or not R is true, and then anything and true is just whatever it was the original thing. It did not introduce a new component to the CNF. Okay, so the first term is not useful. So the outer loop will now increase its index to look at the second term, and then the inner loop has to reset to look at the third term. Do you see how I'm using a double loop to do this? Okay, but basically, this is a double loop, which means the order of the big O notation is going to be the number of components squared, worst case. If you have n components inside the CNF, it will take you big O of n squared time in order to conclude. What are the conclusions? If by the end of this entire thing, I did not end up with a new term, I have to stop. It means there's no possibility of having any new term because I have already tried every single pairing between all the components already. So I have to stop. Or if you're lucky, you can end up with a 0. You can end up with a false. Then you can stop immediately because once you have and a 0, that means the entire thing is false, which means we get to where we want. Improved by contradiction. Is that okay? So I'm not going to ask you guys to write a program to do resolution to prove theorems because it's kind of fun. It's a little bit fun if you want to do it by yourselves. By all means, try to do it. But I would not do it in C or C++ because C and C++ do not have the best string processing capabilities. If you are to use Perl or Python or something like that, I think it will be a lot easier. But you can go ahead and do it if you want to. It's not that involved. You look at it and go like, it may be kind of involved, but when you look at it as smaller steps, it's really not that bad. But the point is, it will terminate, okay? It will only take a fixed number of steps before it can terminate. So let's move on and talk about a little bit of the theoretical limits of something like this. In other words, if I give you 5 variables, what is the worst possible thing that can happen? Okay, so here. I'm going to put that discussion on the mouse pad. Okay, so let's say we have 5 variables. What is the worst thing that can happen with 5 variables? In other words, how many things can I possibly have? What is the upper bound of well-formed formulae that can be in iota? Okay, now 5 is a lot. Okay, so let's shrink it to 2. Okay, so let's say we only have 2 variables. Can someone give me all the possible CNFs involving 2 variables?
4.
Okay, they're a little bit more than 4. Okay, so what you do is you look at the disjunction. Remember, each component inside the CNF is a disjunction, right? So you have a disjunction, which is kind of in the form of a plus. What you can have is, in this case, you have P plus Q, right? You have not P plus Q. Then you have P plus not Q. And then you have not P plus not Q. But that's not all, because we have a few that are kind of extra or special, because you have P all by itself, then you have Q all by itself, you have not P by itself, and then you have not Q by itself. So the actual number of components you can generate out of two variables is actually 8, not 4. Because you have to take into consideration P by itself, Q by itself, and then not P by itself, and not Q by itself. But the big question is it finite? Absolutely finite, okay? Then you look at these things, and you ask, okay, so how many ways can I combine these things into a CNF? Because these are the individual components that can be generated by two variables. Then you can combine these into a CNF. In other words, I can look at this and go like, oh, I can have one CNF involving P plus Q and not P by itself. Okay, that's one CNF, right? I can have not P plus Q, and then the other one is P or not Q. Okay, that's another CNF. So now the question is, how many CNFs can I possibly end up with by having 8 components to begin with? Just upper bound. A component can either be there or missing, right? So that means, the worst case, absolute worst case, that would also have, including conflicting components, is 2 to the power of 8, which is 256. Once again, the big question is it finite? Yes, it is finite. Okay? So given any number of variables, the number of possible CNFs that you can possibly end up with is definitely finite. And that solves that problem of, what if we take a wrong turn by using the wrong inference and keep going in the wrong direction? Because the space is only so big. Even if you take the wrong turn, you will still end up traversing everything eventually. Are there any questions about resolution so far? Questions? Did I end up explaining the one that did prove the contradiction? I think I did. Okay. So are there any questions about the big picture? What this is for? The what, which is what kind of mechanism are we using here, and also the how, which is basically the details of the mechanism. No questions? Okay, so I'm gonna quiz you guys. Why are we talking about this other than it is in the syllabus? And I'm putting the syllabus because it's in the curriculum. It's in the curriculum because it is in the what we call the template class in CID. This is agreed on by all the community colleges, all the CSUs, and all the UCs. So other than those, kind of earthly, reasons, why is this important?
Because it provides a framework for computers to be able to automatically compute through theorems.
Yep, exactly. This is the groundwork for enabling computers to prove theorems. So other than helping you to do your calculus homework faster, why do we want computers to be able to prove theorems? Yep.
Draw a lot of computational power and very hard to.
But why do we want to do that? Why do we want to automate theorem proving in computer science? Computer can do it faster. Okay. Yep.
So we don't have to.
So that we don't have to. But eventually it leads to something, right? In computer science, we can use this. We are not doing this for mathematicians. They can prove their own theorems. Yep.
Automatic debugging, computers debug code.
Verification, okay? Automated verification of programs. That's what we want, okay? Because we want to build bulletproof code. Now, we may not be able to have a computer to write its own code, okay? But at least we can use a computer as a filter, okay? We specify what this code is supposed to do as a long mathematical condition, and then we feed in the actual C++ code, Java code, assembly language code, whatever. And the computer will come up with one of two possible answers, yes or no. Does it pass the filter or does it not pass the filter? If it passes the filter by using automated theorem proving, then we know for sure this code works the way it is supposed to. Okay, there are still potential problems which are basically compiler-based and other tool-based, but for the most part, the code itself is okay. If it comes back as a no, we know the program is not doing exactly what the specification is saying. Now, how is it off from that specification? The program doesn't tell you, it just gives you a no, okay? But it does tell you that, okay, it does not meet the specifications. So that gives you at least that one answer and say that, nope, this is not ready for production. Somebody has to fix it.
Does Microsoft like not do that?
Sorry?
Does Microsoft like not do that or something?
Well, nobody can actually do it because the automated theorem proving is still kind of in research stage. Even with all the computation power that we have now, it is still quote unquote in research stage. So it's not really put into practice yet. Yep.
What's like the timeline on it?
Say again?
What's the timeline on it?
The timeline on
Like how long until that's in practice? Like rough estimate?
the trouble has to do with the theorems, the programs are getting more complex as time goes on. So even though we have more computation power, but the programs that we need to verify is also getting more complex at the same time. So I would say computation power is keeping up with it, but it has not the crossover point has not occurred yet.
But we're able to verify like simpler previous algorithms?
Oh yeah, we can verify very simple algorithms.
Okay.
So in one of my classes in cisp 300, I show people how to. I think I might have done it in this class too. The algorithm to find the maximum of two variables. Did we talk about that in this class? No? Okay. Yes?
We did. Yeah.
We did? Okay. So that one the computer can easily do that one. But when you're talking about the hard bleed problem, the SSL library, that's a lot more complex. So whether we have enough computation power for that particular problem, I don't think we do yet. For practical purposes, we cannot do it yet. Okay. So are there any questions, any other further questions about this? Questions? Okay. So if you have no questions, we are going to finish the next homework assignment on resolution and CNF and stuff like that. And then once we start the next homework assignment, which is Thursday, we'll also do the practice test for the first midterm. And then 1 week after the practice exam is going to be the actual first exam. So the scope of the first exam includes everything up to and including CNF, resolution, and propositional calculus. Is that okay? So that's most likely going to be next Thursday. Or possibly the Tuesday after that, because I do want to give you the solution of the homework, so that you know, okay, this is what I did, and this is the solution, so they can use that for studying as well. So let's just put it on the Tuesday. That is a week and a half from today. Okay. And when is that? Okay. I'm just looking for the calendar in Moodle.
March 7th.
Take it.
March 7th.
March 7th?
Yeah.
Okay, so let's go ahead and schedule the first exam on March 7th. Okay? And I can't look at the big screen like that, the big fonts. I'm going to put it onto the Google Calendar, not Google, but Moodle Calendar. So I'm going to put a new event so that we can see it, right? So first midterm description is up to and including propositional calculus, CNF, resolution, and proof by contradiction. And the date is going to be March 7th. Yep, that's 2 weeks from today. Save changes. There we go. So when you log into Moodle, March 6th should like. Yeah. So that's the right. Is that the right time?
That's April.
March is above you.
Oh. Not paying attention to details again. There we go. Okay, so that's also when proof by resolution is going to be due, but that's based on previous semester's timeline. So ours is going to be a little bit ahead, so you guys will have it due on the 2nd. Right, excellent. So I'll give you guys a choice now because we are done with propositional calculus. So we can move on to predicate calculus, which is based on propositional calculus. But if you think that you have seen enough symbols and theorem proving and stuff like that, we can kind of move on to probabilities and that kind of things, which is a little bit more fun because it has to do with gambling. So do you guys want to chance it? Yes?
Sure.
Okay, so we'll go ahead and chance it and move on to. Okay, so we're going to start with probabilities. So there are certain things that are kind of missing in between. Okay, so I can tell you right here, there's an induction here, more proof techniques and stuff like that. We are not skipping that stuff. Okay, we are going to apply that stuff in discrete probability when it is appropriate. Okay, so I'm not going to talk about proof techniques out of nowhere, in vacuum. I'm only going to talk about proof techniques when we do have theorems to prove. Then we'll talk about, oh, this is proof by induction. And how does it work? It starts with this, and then we do that. Okay? All right. So this part talks about, once again, the homework assignments are not adjusted for this semester yet. You can take a look if you want to, but it is not your homework assignment. So discrete probability has to do with things that are discrete, things that can be counted, they're countable. Okay? Can someone think of something that is discrete? Because probability, for the most part, is continuous, but there are certain things that are actually discrete. Whenever you go to a casino, most of the probabilities involved when you go to a casino is discrete. When you buy a lotto ticket, okay, the probability is discrete. So does it give you a sense of what is discrete?
It's finite.
It is finite. Okay, exactly. So you can actually look at the total number of possibilities, and then the question is, what are the chances that these outcomes may actually may actually be the result? So this is where we get started with all of these topics. And why do you think this topic is important to computer science? Because it sounds like this may be interesting to statisticians or mathematicians, but why do you think it is a part of a computer science class? How do we apply that in computer science? I mean, it seems like computer science is all about things that are completely deterministic, right? You write a program in cisp440, you feed it the same test case every single time, and then the same outcome should come out every single time as well. Okay? Nothing would change. Well, that's only your homework assignment. When you go out to work, what do you think is probabilistic? What kind of problem is inherently probabilistic that a computer science person may need to deal with and solve that problem?
You just have any kind of noisy or unreliable.
Okay, so you can have problems with the input signal, right? There can be noise involved in the process, so what you're receiving may not be the actual thing. Okay, that's one. Anything else? Anything else that is probabilistic and you have to deal with it as a computer scientist?
Deal with humans.
You have to deal with humans, okay? But in what way is probability going to come into the picture in that case?
How often are you going to put the information in that you expect versus how often are they going to put in something that is random?
Okay. What about computer gaming? Because I know there are at least a few gamers in this class. You guys can identify yourselves. What about computer gaming? Why do you think computer gaming may have something to do with probability as well? What is a game where everything is completely? Go ahead.
I was gonna say computer AI behavior and stuff like that.
Exactly, the computer AI behavior. Why do people play PvP or person versus person games a lot more than playing against bots? Why do you think that is the case? Bots get easy because once you understand the algorithm behind the bots in the game, you can counter bots fairly easily, or you can just give up. Because some of those bots are just totally overpowered, okay, in which case it's no fun. And then it can go the opposite extreme where they're completely predictable and there's no fun either. But when you're playing against other people and those people are thinking and they're countering your strategies as well. Okay, so that's one thing. But what do you think probability has anything to do with AI in the context of gaming?
It allows computers to learn from you.
How do you think computers learn? Okay, that's a very good thing. Okay, it has to do with computer learning. But why do you think computer learning has anything to do with probability?
Because it's regressive, so like based on like the actions this person makes, they tend to do this. Say if I always go left and they maybe go right, so maybe now I'm gonna go right because just to throw them off. So like it gives the computer
Increased probability.
yeah,
of success.
the more they see like actions, the more they can interpret what your next action is gonna be.
Because you don't want anything to be deterministic, so you want it to be probabilistic. Okay, but you don't want it to be completely random either, right? You don't want to get into a League of Legends game where the computer controlled character is just moving in a random direction and using random moves, right? Oh, I got my ult ready, let's just do it. But nobody's around you, let's do it. Probability says it's time to do it. That may not be a good strategy, right? Okay, so what I want to do, now this is kind of far-fetched compared to what I'm supposed to teach in this class, but this is something that you might want to look into because it is actually what people do in industry. Monte Carlo. Monte Carlo. Okay, so when you look at Monte Carlo, it comes up with a lot of gambling stuff, okay, which is normal. But you want to look at Monte Carlo algorithms, okay? And there are certain things about this, okay? There's also Monte Carlo tree search. Okay, so this is interesting stuff because what people do is they use computers. They make computer learn, by constructing trees, okay? At a certain point, okay, what do real people do? Okay, there's a 50% chance going this way, 25% chance going here, and 25% chance going there. That can be observed, because you can observe. The computer can observe a human player and just say that, okay, given a particular state, a given scenario, a given condition, okay, what are the chances a person would do this? The chances would go this, the chances would do this, right? Okay, so let's say the player make a particular move. So now you have one branch of the tree. So that will lead to the next state. So in the next state, guess what? Same thing happens, okay? Because now you're in a different scenario, and then you ask those questions. What are the possible moves? And if I observe a human player, what is the probability distribution of making a move like this, or like this? So now you have a tree, but it's not just a normal tree anymore. This tree actually has probabilities associated with the branches. And the computer can construct a tree like that and populate the probabilities pretty easily, okay? Once you know how to classify a node, what you consider to be a discrete condition, you can do it. But now the question is, when it's time for the computer to become the player, to basically counter a person, how do you think the computer is going to do it? You already have a tree constructed based on the observation of a lot of good players. So how do you want the computer to actually play the game now? It's just traversing the nodes, and whenever it goes to a particular node, it would throw a dice. And then based on the recorded probabilities, the computer can now just make a move according to the chances of making that particular move. In other words, a computer can learn and mimic human strategies by observing, learning, and applying what it has learned. So if you're interested in that kind of thing, this is what you want to look up. Monte Carlo tree search. It is being used in a lot of actual heuristic problem-solving situations. Let me think whether I can actually say this or not. Okay, I'll just kind of obfuscate the actual scenario, but I can tell you this is actually used by national labs to do some really serious stuff. But I'm going to hide the actual things that they're doing because I'm not really sure whether I can say that or not. Okay, so I can apply that to I'm trying to think about how I can obfuscate.
Self-driving cars. Self-driving cars.
Self-driving cars. I don't think you want your self-driving car to use a Monte Carlo approach. It has to do with classification of whether something is in a particular classification or not based on the observation of sensors, okay? But there are actual problems in real world where people use Monte Carlo approaches to solve problems. So that is why, discrete probability, the stuff that I teach in this class is not going to be like that, okay? Because I can only teach lower division classes, relative to a 4-year university. But eventually, this stuff all leads to things that are actually useful, things that are actually in use by national labs and by other professionals in the computer science realm. So that's the connection. It's always important to understand the connection. Okay, so one reason why we also want to study probability outside of this class is, well, if you go to a casino, how do you know whether you should gamble or not? Okay, you look at the jackpot of the super lotto. Okay, so how do you decide it is time for you to kind of, okay, I'll try my luck. Here's $10, I'll buy 10 tickets. Okay, how do you know, right? Okay, first question is, can we actually know when it is a good time to buy a lotto ticket? Well, the answer is kind of yes or no. It depends on a very, very important assumption. Okay? Is everybody else going to think like you? That's the question. That really is a big question. Because if everybody's going to think like you, then the approach is not going to work anymore. And I will show you why. Okay, so I only have like a few minutes left. So instead of actually going into the detail and show you all the factorial, talking about that stuff, I'll just give you the equations. Or you can go to the website. You can go to the Lotto website, and we are not going to come up with the numbers. Okay. This is not California Lotto. So we want to look for California Lotto. There we go. Now, when you go to the Lotto website, you can go to a particular game, let's say Powerball, and they will give you the chances already, number, frequency. Okay. In other words, you don't even have to derive these numbers, not number frequencies, but we want to look at how to play, and in how to play, they will, I think, required by law, they give you the odds. Okay, so this is already calculated for you. Odds 1 in blah blah blah. So if you want to win 5 of 5, and also the Powerball, the chances is 1 over 292 million blah 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 blah. I think the jackpot, I drove over the highway billboard, and I think the jackpot is like 400 something million now. Okay, so the question is it a good time to play? Well, you cannot just use you cannot just use the probability here to make your decision, because you really have to ask a tax expert as well first. Yep, go ahead.
It also depends, like, how much is a ticket?
I think it's $1. Okay, so the first thing you need to ask is a tax expert and say, okay, what is the best way to get this money out? And even using the best method, how much taxes am I paying? Because if the jackpot is $400 million, and let's say you are the fortunate one who actually get $400 million, okay? Well, guess what? Uncle Sam wants his cut too. If you spend $400 million right away by buying like 3 or 4 of your Ferraris, then by next year tax season, you're in big trouble. Because then you'll be owing IRS and also franchise tax board millions of dollars. But the most important question is the one that you cannot predict. When you think it's a good idea to buy a lotto ticket because the number makes sense, is everybody else going to do the same thing? Because with a lotto ticket, they can issue the same numbers or the same ticket to multiple people. They can make multiple winners of the jackpot. And that is the one thing that is really, really hard to model. How many people would think like that? So how many tickets will end up eventually be purchased? And as a result, what are the chances that you'll be the only winner? What are the chances that you'll be the co-winner, and so on and so forth? That is the most difficult part of modeling when it comes to lotto tickets. So typically when you look at gambling, you look at the organization organizing the gambling. If they seem to be making money, it's not a good idea to gamble. Because that money comes from somewhere. All right, so this is the end of today's class. On Thursday, I will give you a new homework assignment on resolution, and then we'll continue to talk about discrete probability.